If you remember, in this chapter, we were discussing some laminates and made of paper, metal, or other materials that we are trying to put them on top of each other. And the way actually we are joining them might be quite different. Sometimes we first form them and then bond them together, or we first bond these sheets together and later do forming operation. And we discussed all these advantages, disadvantages. And on this slide, as you see, we have another type of bonding. It's called as thermal bonding, and it's a very popular process in this sheet lamination approach. What we are doing in this case, in thermal bonding, we will have diffusion bonding. Since it's an example, the materials will go inside each other and we will have a rigid connection between the sheet metal or sheets, other types of material. And for that purpose, we may use lasers. Do you remember laser spot welding or other spot welding operations? Yes, let me, why this one is not working. Let me switch to the pen here. Okay. So if these are some layers in the spot welding, you might have just you may be welding the materials from specific points, not completely, but such spots might be present, and with the help of it, you can join these sheet metals together. Or you may use some brazing techniques. I don't know whether you remember, it's a joining process, and you need to use some special material, and you'll distributing this brazing material in between these sheet materials. So you have a little gap in between the two layers. You'll distribute some specific material here, and then by heating them, these two materials, these two layers will be joined together. And for the metals, we may have some thermal bonding processes, but usually we prefer to have form and then bond approach. Why do you think this is preferred for the metal parts? If you're going to produce metal products by using sheet lamination processes, as you see here, it's written that form and then bond processes preferred. Why do you think is that? Why don't we perform first bond and then do the forming operation?
Cutting process daha kolay olacağı için mi layer by layer?
Might be other issues. We have several reasons. So do you remember what happens if you do forming on the laminated particles?
Shrinkage.
You may do some damage on the previous layers, right? If you are exactly doing the forming operation after the bonding, that will result in some damage in the previous layers. But if you do the machining first and then bond it, then you don't have the risk of actually damaging the previous layers. This is a nice advantage for the metals. Another thing, if you first form and then bond, then that means you might have some cavities, right? Some internal features are easy to obtain with form and then bond approach. Otherwise, in the bond and form approach, you can have some cavities, but it will be quite difficult to close and have some complicated features. But with form and then bond approach, you can have complicated interior shapes, interior structures. Let's briefly look at a variation of sheet lamination process. This is called as shape deposition manufacturing. And we cannot clearly say that it's a sheet lamination process. It's a kind of a combination of some other additive manufacturing process and sheet lamination process. So with the help of other additive manufacturing processes, we obtain near net shape and then do some finishing operation by machining. So in summary, you deposit some material and then do machining. And obviously, the accuracy, the quality, material will all depend on the type of manufacturing processes you are using. And if you have some overhanging features, obviously, you need to use some support structure, and you need to have high skilled labor to perform this specific process. This is the fundamentals. You deposit, this is a cycle. You deposit, shape it with your cutter, and then embed some particles. This is an embed some components, a very nice feature of shape deposition manufacturing. You may embed some sensors, actuators, electronic boards. So it's a nice feature. You can embed such a part inside and then deposit another material and again do the machining. And you can continue this process as many times as you like, but we don't have actually exactly a commercial system employing this approach. And then we have another variation of sheet lamination processes. It's called as sheet metal clamping. As the name implies, we will be using sheet metals, but they will not be joined together with adhesives or other thermal bonding processes. We will be simply using clamping forces. And in order to have a proper clamping operation, we need to have some actually bolts, use some bolts and special clamping mechanisms so that the accuracy will be higher. And the advantage of this process is that it's very inexpensive, since just you need to do is to machine the layers first and then put them on top of each other, like in the case of stratal conception. Another advantage is that you can easily disassemble them by opening your bolts. Actually, you have bolts or the screws. You can simply remove them, disassemble, and do modifications and then assemble. Another advantage, since it's quite disassemblable, you can easily recycle the unnecessary portions. And the important thing is that once you are clamping, these clamping forces should always be perpendicular to the laminate interface. So if these are the layers, these are the sheet metals, then your clamping force should be always perpendicular to this laminate interface. And this is the interface between the laminates. Here's an example. It's from Fraunhofer Institute. You have these sheet metal layers, and you can see we have some guideways here. Probably they are putting some rods inside so that it will be easier to align these sheet metals. Any questions, guys, up to now? We'll be now talking about different topic. Actually, the rest of this part, this chapter is on ultrasonic consolidation, or these days we prefer to use the term ultrasonic additive manufacturing, UAM. And as the name implies, we need to use some ultrasonic kind of waves, and with the help of them, the sheets of metals or other kind of materials will be joined together with the help of ultrasonic welding process. And we have a company actually working on this process called Solica. They started working on it in 2000. And the process, the whole process can be named as a hybrid process, since they first do a kind of an ultrasonic welding operation. We can assume that this part is additive part. And then after the sheet metals are joined together, and then we do some subtraction operation. So that's why it's called as a hybrid manufacturing process. And at the beginning, as a base, you need to heat the plate so that your sheet metals will be stick to it, will be joined to the base material. And later, you need to do further post-processing to get rid of this base material. And for the joining or for the welding operation, we are using ultrasonic vibration, and we will be discussing the details. There is a rotating sonotrode, which is responsible for joining these sheets of metals, and its frequency is around, and actually exactly at 20 kilohertz. Now let me show you an animation. As far as I remember, it should be the animation. Yep. Any questions, by the way? Let me share the screen. Okay. Let me start from beginning. Yes, this is Sonotro bringing another sheets. 4 sheets actually will be, or this one, 3, I don't know, but usually they laminate 4 sheet metals and then later they do machining. But in this example, they are laminating 3 of them and then doing machining operation. You see they have an internal feature, right? Since we are laminating a continuous material on the opening regions, on the channels, you can easily obtain such internal features. But I think they are going to cut it. They don't need to cut it if you want to have a hole inside, a kind of an internal feature, but depending on your case, you may do machining or not.
Hocam soru sorabilir miyim?
Sure.
Az önce tam dediğinizi doğru mu anladım emin olamadım da mesela bunda 3 layer attıktan sonra kesme işlemlerine giriyor. Bu sayı sabit mi oluyor?
Yes, depending on the machine you have, the number is usually constant. Since the tool actually is not capable of just machining a single layer. Since it's a very thin layer, that's why they usually have 3 or 4 layers to be machined.
Peki internal feature'larda o kadar yüksek bir şey yapmamız gerekmediği durumda ne yapıyoruz peki?
But the thickness of the metal is very low. You may have just 1 millimeter, maybe less than that, depending on the type of sheet you are using. Probably that will be enough.
Tamam hocam, teşekkürler.
You're welcome. So these are the fundamentals of, where is my point? Okay. Fundamentals of ultrasonic additive manufacturing. And obviously, while we are doing a kind of a welding, ultrasonic welding, we will have metallurgical bond between the layers. Here's another nice illustration. You see we start with a heated base. So this is important, otherwise your foil, your sheet metal will not be stick to the base platform. And depending on the thickness of your part, you may have many sheets on the same layer. As you see, right now we have 4 of them. I think it needs 3 more, so 7 sheet metals will be spread on this layer. And while spreading it, this sonotrode is rotating obviously, and it's applying kind of also a force. This is force applied by the sonotrode. This is side view, by the way, the previous layer and the next layer. You see with the help of the vibration, high frequency vibration, we will have a kind of a connection in between the layers. And this is a close-up view. As you see, this is 20 micrometers, and we will have metallurgical bonds between the layers. And this is another side view. Our sonotrode is rotating and also moving to left, and it's actually laying out this sheet metal.
Hocam bir şey sorabilir miyim?
Yep.
Buradaki üretim 2.5D tarzında mı? Yani overhang feature'larımızın olması mümkün mü acaba? Örnek veriyorum, ilk layer'lardan çok aldıktan sonra yukarıya yaptığımız büyük layer'lar için herhangi bir support'a falan ihtiyacımız olur?
No, but you need to be careful about the force which is applied on the sonotrode. You may have, let me try to draw a cross section. Assume that you have a kind of a first layer and then have another layer like this one. So the first layer, second layer, and you may have the third one like this. And in this example, we have a kind of a channel here, but while laying out your sheet metal, your sonotrode will be passing through. It's rotating, and obviously it's moving to left. While it's moving to left, since you're always applying pressure on top of the sheet metal, you should be careful about the width of this gap. If it's too much, then probably you will deform this region, and instead of having a flat region, you may have such a banded part. So if you have an actually larger width, then that means you may use some support structure. But the difficulty is you cannot easily remove that support structure. So you should keep in mind the solution might be is that you may remove or decrease the actually amount of force you are applying at this region. So let's have a kind of an graph for position and force. So you may have a constant force and then decrease that force while you're passing that channel and then increase it again. That might be a solution in order not to have such a banded region. There's another question. So what these ultrasonic waves are doing actually, this is ultrasonic welding. So with the help of this high frequency vibration, we will have some plastic deformation. Once you have plastic deformation, then you can easily join these materials together. We are not heating, we are not doing any kind of melting, but they will be in the plastic zone, and you can join these sheet metals together or other kind of materials together. It's also done for polymers, but we are mostly talking about metals. Any other questions, guys, on these fundamentals? Yes, Umut?
Sonotrode constant force mu uyguluyor acaba? Ben o şeyin vibration nasıl ortaya çıktığını anlayamadım.
We have, let's say this is the frequency, say some hertz, and we have obviously an amplitude, but not that much. And the frequency is exactly at 20 kilohertz. And we need to be applying force, otherwise it will just pass through the sheet metal and it will not be able to join the parts together. Force is an important issue, but the amplitude is not much. It's not moving. Actually, you cannot see the sonotrode moving in the Z direction. It's very little, around some micrometers.
Teşekkürler.
Welcome. So in the example, in the animation, we have seen that it was laying out 3 sheet metals and then doing machining, but for most of the time, companies are preferring to use 4 layers. They deposit 4 layers of metal foils and then do machining. And we call these 4 layers as one level in ultrasonic consolidation or ultrasonic additive manufacturing. So after you have one level, then you need to do machining. You do machining around the contours. So you repeat these processes until you have the final part. So you can say that this is a kind of a bonds and then form process. Let's have a look at this video. Let me share it. So it's from Oak Ridge National Laboratory in the United States. The company is Solica. This is again an animation, but a much better one. Machining. And then sheet metal is deposited. Now you can see the sonotrodes underneath. And the advantage of this process is you may have some components. Actually, components are quite challenging, but embedding wires is not that difficult. You can have such wires inside your part. So now you can see the sonotrode, and it's vibrating as you see while doing this vibration. You have metallurgical bond between the layers, and you'll have a stronger product. And the amplitude is, as you see, not too much. Another advantage is that you may have different types of metals in the same product. As you see, initially we have some steel underneath, but right now it's depositing copper, and we have such nice features. Another layer of different material, another cable, and you can have complicated channels and close the top of these channels, which is not possible in the conventional approach. Any questions, guys, on these systems? There's a question. So the foils are actually simply bonded together. We don't have machining first, but after one level is completed, we do the machining. So in overall, we can say that it's a bond and then form process, but the interior is not important for us. So obviously, since we are using CNC machining, the overall accuracy and the surface quality will be depending on the CNC machining. And if you are using proper tools like nose tools in your CNC machine, you may eliminate the effect of staircase. For instance, you have such a side surface. These are assumed that some layers. And if you use a proper tool, a nose tool like this one, then you can eliminate this staircase effect, which is a nice property of this machining. And you can obtain very complicated parts, functional parts, having wires, compacted features inside. You may have multiple materials. Even if you be careful enough, you can embed some special sensors, actuators, and other optic products. Another thing about this approach, another maybe drawback, you don't have a special support structure mechanism. As we discussed in the previous slides, if you have some critical internal features, wider internal features, and maybe overhanging features, you need to think about the support. Otherwise, there might be deflections on your overhanging and internal features. Let's have a look at this example. Our aim is to obtain actually a panel having honeycombs inside. And for that purpose, we are using ultrasonic consolidation, and we will be using aluminum 3000 series material. And we start with a heated base. And now you'll see that we'll be adding these sheet aluminum one by one, and then do some machining, trimming operation. As you see this time, I think they are again doing machining after 4 layers, but they do surface machining after 40 layers, which means that the fabrication is over and they can clean the top surface of the product. And probably we will not, they don't have any openings, but due to the, I think this is not the final product, at the end of it, they plan to close these honeycomb features. Any questions, guys, about this example?
Hocam bir şey soracağım da.
Yes.
Bu CNC milling de genelde soğutucu sıvı kullanılıyor ya ısınma problemleri için ya da işte dimensioning için. Bunda öyle bir sıvı ya da başka bir şey var mı? Yani o ısınma problemini nasıl aşıyorlar?
You can use them. We don't have any limitation. You can use even hydrogen cooling or water cooling, oil cooling. It's all possible. We don't have any limitation. Another question on chat, how do we deal with the height coming from embedded wires, wiring and sensor? Probably, if it's a big problem for you, you need to have extra material around, or once you have enough material on top of each other, with the help of ultrasonic welding, probably you will not see them after, let's say, 10 layers. It will not be a big problem, and I think the thickness of these wires are not too much. So now let's discuss the quality between the layers. The ultrasonic consolidation bond quality, or we can say ultrasonic additive manufacturing bond quality. We have two parameters defining the quality in these processes. The first one is linear welding density, and the other one is part strength. Obviously, you can obtain, compare the strength of your part by doing some experiments. But for the linear welding density, we need to have a cross section. This is actually the base plate, as you see. We have one layer starting here, another layer here, another one here, another one. So we take a cross section of the product and then check the welding density. So how we do it? Assume that this is the width of the part we are looking for, and you can have a look at the impurities on this line. At the interface between the base plate and the layer, we don't have any, as you see, openings. But if you look at, for instance, the interface between layer 1 and layer 2, we have some impurities, we have disconnected regions, and you can compare the percentage of these regions with respect to the length of this cross section. And by using that, we can obtain easily the linear welding density. And obviously, it's 100% for the interface between the first layer and the base, but it's less in the upcoming layers. Actually, it's the least between the third and the fourth layers. Maybe around 60% or 65%, I don't know. Another thing is that if you look at the top surface, we have bumper regions, right? This is the top surface, and why do you think we have such a case? It's just due to the force applied by the sonotrode and the system. And the surface roughness actually depends on the quality of your sonotrode and also the amount of force you are applying on the part. So let's have a look at some basic history of this process and other fundamentals. It was invented in 1950s, and people actually, not the whole process, not the additive manufacturing process, but the welding process was invented in 1950s, and people are using this ultrasonic welding, metal welding process in different industries, especially in automotive and electronic industry. The thing is that we don't have high temperature. We are not joining the metals by heating them. We don't have thermal bonding. So this is the main advantage, and that's why people are preferring to use it, especially in electronics industry. Since if you have high temperatures, probably you're gonna damage the electronic components, but if you just have an ultrasonic vibration or ultrasonic welding process, you will not have high temperatures. And the maximum temperatures in this process are usually about the half of the melting point temperature of the material, or usually less than that temperature value. And in this process, in this welding process, the bonding is obtained by mechanical interlocking. The parts will go inside each other, or if you have interface materials, they will be melted and joined together, or you might have some plastic deformation and diffusion may happen, or atomic forces across your new metal surfaces may help you join these sheet metals together. Another advantage we have actually less thermal stresses and less thermal deformation in this ultrasonic consolidation or welding process. Since the temperature is not high, so the possibility of generating such residue stresses, thermal residue stresses, is very low compared to other joining processes. Here you see an example. Yep.
Bir şey sorabilir miyim? Metal sheetlerin bu kadar ince mi olması gerekiyor 150 mikron kadar bu welding işlemini yapabilmemiz için?
Yes, otherwise you cannot apply the vibration to the interface clearly. If the thickness is too much, then you cannot join them. You cannot obtain this mechanical interlocking or diffusion. You cannot start plastic deformation at the interface.
Teşekkür ederim.
So here you see we have sheets of aluminum, bottom layer, top layer, and in between we are embedding a stainless steel kind of mesh. It's a very specific case. I think this should be from a study, a research. They are trying to embed such a stainless steel mesh in between. And if you look at the interface here, in some regions we have metallurgical bonds, but in some regions we don't have any. For instance, here in the white arrows, we don't have any metallurgical bonding between aluminum and the stainless steel. So they put this actually mesh just to increase the quality of bonding between aluminum layers. But it's not a must. It's just for research. They check whether this one is increasing the strength or not. So what are the basic conditions for to have bonding in the ultrasonic consolidation? First of all, you need to have clean surfaces. If you have any oxidation, other, let's say, particle, dust on your surfaces, then you cannot have a proper bonding between the layers. This is the first thing you do. You need to have a clean metal surface. And you shouldn't have any bumps actually on the metals you have, on the sheet metals you have. You should make them clean and smooth. Once you have done these, actually, once you satisfy these initial conditions, then you can start plastic deformation with the help of your ultrasonic excitation and the normal forces you have on the sonotros. So for that purpose, in the cleaning stage, you need to remove oxides on your surface. Otherwise, as we discussed, you cannot start the plastic deformation. So we have such a statement. Let's read it and let me ask you why it is stated like this. Due to a significant hardness difference between aluminum and aluminum oxide. So we have aluminum and aluminum oxide. And the thing is that there is a huge difference between the hardness values of the pure aluminum and the aluminum oxide, which is in which case we have oxidation on the surface, and that's why these sheet metals are usually preferred for ultrasonic welding process. So why do you think is that? Why do we prefer to have aluminum if you just look at the initial statements? Why hardness actually helps in ultrasonic welding process? No answer? Okay. Then let's have a look at other properties. So once you apply high frequency vibration, then some of the properties of the metals will obviously change. And some of these properties will be nice for joining. For instance, if you have huge vibration, then you will be doing a kind of acoustic softening. And with the help of it, it will be easier for us to start the plastic deformation. With less forces, we can start the plastic deformation. And another thing, you may have actually some defects increase. This is not a nice property. You may have some cracks inside your microstructures, or you may have some diffusities, which is a nice property. The microstructures or the parts will be joined in a better way. So now let's have a look at some parameters in this process. how we are going to optimize these parameters to have a proper ultrasonic consolidation or ultrasonic additive manufacturing process. What are the important parameters? The first one is the amplitude of our oscillation, the value of these oscillations, the normal force we are applying on the sonotrode, the speed of the sonotrode, and the temperature in the environment, and also the temperature of the sonotrode. And they will obviously be affecting the quality of overall bonding between the layers. So without, let's discuss some of these. What happens if you have high speed? What do you expect? Are you expecting a better bond or a worse bond?
Worse.
Usually it will be worse if you do not actually spend some time on a specific point. Then that means you'll not be applying enough energy to that point. It's very similar to other, let's say, polymerization or melting processes. We have a critical value for the energy. If you do not go over that critical energy value, you cannot join the sheet metals together. So depending on your other values, you mostly have actually a lower speed. What about the normal force? Can you comment on the normal force, how it's going to affect the quality? For instance, what happens if you have less force?
Layers will not bond, but if the force is too much, it will deform, it will harm the product.
Yep, you're exactly right. So we need to find an optimal force value. And if you have too much, for instance, force, the surface quality, the surface roughness will be higher. And in the next layer, that high surface roughness value will not let you actually join the new sheet metal to the previous one. So they should be all optimized. These parameters should be optimized to have a perfect bond between the layers. Let's have a look at the first one, the amplitude of the oscillations. And now, as I mentioned, the energy input is quite important. So this level should be above a critical value. Otherwise, you'll not be able to start a deformation and the metals will not be joined together. And the energy is defined actually by affected by the amplitude and the frequency of these oscillations. So it's an important parameter. It's defining the ultrasonic energy we have in our systems. So since the frequency is constant, we said that it's mostly equal to 20 kilohertz. We can assume that as a constant value. So if the frequency is constant, then we can only play with the amplitude of the oscillations to adjust the amount of energy actually we are applying on the parts. So this is the only thing we can play in terms of ultrasonic energy. And we can say that depending on the material you are using, you may have higher amplitudes or lower amplitudes. If it's a soft metal, then with low amplitudes oscillations, you can do the joining. But if it's a difficult material, then you need to increase your ultrasonic energy by increasing the amplitudes of your oscillations. These are the same things we discussed. So now let's have a look at the normal force, the importance of the normal force. Obviously, it's the load we are applying on the sonotrode, on the moving, rotating sonotrode, and the optimum value of this force is highly important to have metallurgical bonds. We shouldn't have much or higher, lower. So obviously, as we discussed, as your friend pointed out, if you have lower or higher forces, then the quality of your bonding or the linear welding density will be low compared to the optimum value. These are the things we discussed already. If you have higher forces, then the previous layers or the top surface will be deformed and the upcoming interfaces will be affected. Now let's briefly discuss the welding exposure time. This is actually defined by the sonotrode travel speed. So as I pointed out in the earlier slides, if your sonotrode is moving at a very high speed, then that means your welding exposure time is low. And once this value is low, then that means probably you will not be able to start the plastic deformation and we will not have a bond between the metals. So again, you need to optimize these this speed value to a proper exposure time and proper bond between the layers. So same things. And another issue, if you have over inputs, which means that if you have lower speeds, you will be increasing the ultrasonic energy you are applying on the layers. And if that's the case, you will be deforming the layers, and also you will be decreasing the fatigue life of your product. Now we have pre-temperatures. If you have let's say ambient temperature around 100 degrees or 200 degrees, that may help you join the parts easily. Actually, this ambient temperature depends on the material you are trying to join. If it's an aluminum, obviously you should keep it very low, but if it's a steel, you may increase maybe to 300 or 400 to make your joining easier. So you see, for instance, for aluminum, the ambient temperature is usually around 150 degrees. With the help of it, you can reduce the flow stress, which means that with low forces, low applied forces, you can start the plastic deformation. But if you have high ambient temperatures, then we have the problem of actually foil sticking to the sonotrode. So if the sheet metal is sticking to the sonotrode, then that means you cannot continue with the additive manufacturing process. You should stop it and clean your sonotrode, and this will cost you a lot. Another issue about high temperatures, if you have some embedded electronics, other components, actuators, sensors inside your part, then you can harm these products, and again, that will cost you once again a lot. Any questions, guys? Now let's briefly talk about the defects we have in the microstructure or on the surfaces. First of all, you might have some voids between the interface, and it's the most common problem. It may happen between the layers, or it may happen between the neighboring foils on the same layer. So if you remember from one of our initial sketches, illustration of ultrasonic consolidation, if this top view, once the width of your part is too much, then you may have, let's say, 3 sheet metals actually deposited on the same layer. But while you are depositing, probably you will have some gaps here, right? It will be quite difficult. You may have kind of a gap in between the neighbor foils, and this is called as a type 3 defect in ultrasonic consolidation or ultrasonic additive manufacturing. Then we have type 1 and type 2 defects. These are between the layers. So if this is a side view, so that these are some layers, some foils. And again, depending on actually wrong parameters you are using, you may have some roughnesses on the layers, and this will result in some gaps, or you may have some specific damaged areas. If it's a damaged area, then it's called as type 2, and this damaged regions are just due to the high energy input. You may have other problems like surface roughness or insufficient input energy, or you may have some oxidation between the layers. These are all called as type 1 defects. Now let's have a look at these. This is the first type of defect, and you can see some surface oxides here, and these are actually resulting in such irregular shapes between the layers, and this part will not be able to join to the previous layer. And if you look at our type 1 definition, it's due to the foil surface softness, insufficient energy, or oxide layer. So we have oxidation here, and that's why it's called a type 1 defect. And then we have type 3 defect, as I have drawn, is this is a top surface of the part. We have some foils actually deposited on the same layer, and as you see, this one is a bit shorter, and we have some gaps in between. They are all type 3 defect. The gap we have between adjacent foils. So how we are going to eliminate these defects? Since these defects are obviously affecting the strength of our product, so we need to remove them by doing some modifications on the parameters, or maybe using some specific equipment. So what we are going to do to increase the strength, we need to first increase the linear welding density. The interface between the layers should be proper. And another thing we can do is to minimize the type 3 defects, which was the defects on the top surfaces on the same layer. If you have gaps between adjacent foils, then it's called as type 3, and we can simply eliminate it by properly depositing these foils on the layers. So once you optimize your parameters, you can actually somehow decrease or maybe totally eliminate type 1 defects and type 3 defects. They can be minimized, but if you have fully optimized parameters, we can totally eliminate type 2 defects. Why do you think is that? We don't have full control on type 1 and type 3, but we can totally get rid of type 2 defects if you have an optimized parameters. So what do you think is that? Let me go back to the definition of these types. So we are stating that type 1 and type 3 can be decreased once you have optimized parameters, but we can eliminate type 2 totally. Can anyone comment on this?
Hocam enerji inputuyla alakalı olduğu için onu kontrol edebiliyoruz, o yüzden mi?
Yes, for type 2, since once you optimize the amplitude of the oscillations, the force, the speed, you can easily eliminate type 2 defects. But what about type 3 and type 1? Why can't we just eliminate them totally by adjusting our parameters?
Hocam çünkü surface roughness bizim kontrolümüzde olan bir şey değil, ya da iki adjacent şey arasındaki boşluk da bizim kontrolümüzde değil.
Yeah, these are all not related to the parameters we discussed. They are depending on the quality of foils you have and the oxidation you have on the foil, so we cannot easily control them. But once you have sufficient input energy, you may decrease, but you cannot totally eliminate it. And regarding the third one, if your foils again are, let's say, tilted a little bit, you may have gaps between the adjacent foils. So again, it's quite difficult to eliminate the type 3 defects totally.